Welcome to MEB. This is episode 11, Physical Constraints and Process Specifications. In the last episode, we ended up in the frustrating position of not being able to solve for any of the unknown variables, despite having worked hard to derive all the material balances. In this episode, I'll discuss some other possibilities for equations that we could add to the system of equations to get us closer to being able to solve. The first type of equation is one that I alluded to several times in the last episode. A physical constraint says that the composition of every stream must add up to 1, or 100%. Mathematically, we say that the sum of xi, meaning mass fraction, or the sum of yi, meaning mole fraction, equals 1. Here, the subscript I is referring to different species within the same stream number. Going back to the example from last time, I could have written a physical constraint on stream 4, since the composition of ethanol and water are unknown. The physical constraint is then 0.25 plus x4e plus x4w equals 1. This is indeed another independent equation that I can add to my system of equations. Generally, you can write a physical constraint for any stream that has 2 or more unknown composition variables. However, unfortunately, this is the only physical constraint that I can write for this particular example problem. The composition of the input stream was completely specified by the problem statement. So, while it is still true to say that the composition adds up to 100%, the equation doesn't provide any new information because we already know everything. Similarly, the compositions of methanol and ethanol in the top stream were given. Remember in the last episode that I just mentally worked out that the missing portion was the 25%. If you think about what I did, I solved the physical constraint already. Also note that you cannot write physical constraints on flow rates. In the middle stream in our example, there is no such physical constraint because the total flow rate of a stream does not have to add up to any specific number. Alternatively, instead of labeling the variable x4w, I could have said that the composition of water in this stream is 1 minus 0.25 minus x4e. Effectively, this method reduces the number of unknowns by 1 instead of increasing the number of equations by 1. Either way is valid, however you must be careful to make sure that you don't do both. If you label it this way, you've already used the physical constraint and you can't use it again. Another type of equation that you might be able to apply in certain cases is a process specification. This is a special phrase in the problem statement that describes the relationship between process variables that only applies in the specific instance of the problem. Let's look at 3 separate examples of what a process specification might look like. Imagine the problem statement had said, the total flow rate of the middle stream is 1/3 the flow rate of the input stream. Using the variables on the diagram, could you translate this process specification into an equation? When I'm deriving equations for process specifications, I find it helpful to focus on some key words. The word is should be interpreted as an equal sign. The word of should be interpreted as a multiplication. Therefore, the total flow rate of the middle stream, which is the sum of M3M plus 300 plus M3W, equals 1/3 times 1,500. Let's try another one. What if there was a process specification that says there is twice as much water as there is methanol in the middle exit stream? Pause the video now to see if you can derive the equation correctly. And I'll bet that you said either one of two things. Either 2 times M3M equals M3W, or M3M equals 2 times M3W. Which one is correct? These types of process specifications are tricky. My tip is to plug in a number just to see what happens. For example, what if the flow rate of methanol was 100 kilograms per hour? The equation on the left side would say that the flow rate of water is 200 kilograms per hour, while the equation on the right would say that the flow rate of water is 50 kilograms per hour. Looking at the process specification again, it says that there is twice as much water as there is methanol, which implies that there should be more water than methanol, and therefore the version of the equation on the left is the correct one. Okay, one more example. What if the process specification was 40% of the water that enters the process exits the process in the bottom exit stream? Be careful with this one. A common mistake that I see all the time is to say that X4 water equals 0.40. The process specification does not say this. Instead, use the key word of, meaning multiplication again. The water that enters the process is 1,500 kilograms per hour times 0.20. 40% of this means that I should multiply this by 0.40. Then, if the bottom stream contains this quantity of water, I set this equal to M4 times X4W. When it comes to deriving the equations for process specifications, my advice is to read the specification several times until it starts to sink in. Break the phrase up into parts, and then write what you think is going on. Finally, reread the process specification again, and double-check that the equation that you wrote makes sense if you plug in a number. Episode 11 Learning Objectives. Now that this episode is over, you should be able to 1. Determine how many physical constraints may be written and derive the equations of the physical constraints, given your complete labeling of a block flow diagram. 2. Write equations corresponding to process specifications in terms of your unknown variables. That will conclude this episode. As always, thanks for watching, and I'll see you next time.